The mystery of tornadoes. Tornadoes are some of the most dramatic and destructive forces in nature. They appear with terrifying speed, carve paths of devastation, and disappear almost as quickly as they formed. To many, they look like random acts of chaos. But in reality, a tornado's birth is a carefully orchestrated process of physics and atmospheric dynamics. For centuries, humans could only watch and wonder. Early settlers on the American plains told stories of dark funnels racing across the horizon, but no one knew why they formed. It wasn't until the 20th century, with the rise of radar technology, storm chasing, and computer simulations, that we began to understand how they emerge from powerful thunderstorms. Even today, scientists are still piecing together the final moments of a tornado's birth. We know the main ingredients, but the precise trigger that causes a storm to unleash a twister remains one of the biggest mysteries in meteorology: the essential ingredients. Not all thunderstorms create tornadoes. In fact, most never do. For a tornado to form, the atmosphere needs three key ingredients: moisture. Warm, humid air near the ground provides the storm with its fuel. Instability. This refers to the tendency of that warm air to rise rapidly through cooler, denser air above it. Wind shear. A change in wind speed or direction with height, which helps create horizontal tubes of spinning air. When these conditions align over a large region, as they often do in the Great Plains of the United States, the stage is set for a dangerous type of thunderstorm called a supercell. The importance of wind. Shear. Think of wind shear as the invisible hand that twists the atmosphere. At the surface, winds might be blowing from the south, bringing in warm, moist air from the Gulf of Mexico, while higher up, strong winds from the west or southwest sweep across the sky. This difference in speed and direction creates long, horizontal cylinders of rolling air. Under the right circumstances, the updraft of a powerful thunderstorm can tilt these rolling tubes upright. Once vertical, the air begins to spin like a giant top inside the storm. This rotating core is called a mesocyclone. The mesocyclone is critical. Without it, most tornadoes simply cannot form. The stronger and more organized the rotation, the higher the odds that a supercell will produce a tornado. The supercell engine. A supercell is a special breed of thunderstorm. Ordinary storms often die quickly as cooler air from rain collapses the updraft. Supercells, however, can last for hours. Their rotating updraft acts as an engine, pulling in warm air at low levels and sending it high into the storm's towering top. This self-sustaining cycle keeps the warm inflow separate from the cooler outflow, allowing the storm to keep feeding itself. Inside, the mesocyclone churns like a massive rotating column, setting the stage for a potential tornado. Some of the largest and most destructive tornadoes in history, such as the 2011 Joplin tornado, were born from these supercell monsters. From mesocyclone to tornado. For years, scientists believed that tornadoes simply dropped down from the mesocyclone above. In reality, the process is more complex and often begins closer to the ground. As the storm matures, a surge of cooler air descends behind the updraft, known as the rear flank downdraft, RFD. This air rushes down, hits the ground, and curls around the rotating mesocyclone. The interaction between this cooler descending air and the warm, moist inflow intensifies the spin near the surface. Essentially, the tornado is born when the mesocyclone's rotation gets stretched and focused all the way to the ground. The role of pressure drops. One of the most fascinating parts of tornado science is the dramatic drop in pressure at the center of the forming vortex. As the spinning column stretches and tightens, air is drawn inward and speeds up, much like an ice skater who spins faster by pulling in their arms. This low-pressure core cools the air, causing water vapor to condense into a visible funnel cloud. At first, the funnel may hang from the cloud base without touching the ground. But as the vortex strengthens, it descends lower. When it finally makes contact with the surface, the tornado is officially born. Touchdown, the birth of a tornado. The moment the funnel cloud connects with the ground marks the tornado's touchdown. At this stage, winds can accelerate to astonishing speeds. In the strongest EF4 and EF5 tornadoes, over 200 miles per hour, 322 kilometers per hour. The tornado acts like a vacuum, pulling debris, dust, and even large objects upward. Tornadoes vary greatly in size. Some are skinny ropes a few dozen yards wide. Others grow into massive wedges more than a mile across. The size of the funnel doesn't always indicate its strength. Small tornadoes can be incredibly intense. Rapid formation. One reason tornadoes are so dangerous is how quickly they can form. Even with all the right atmospheric ingredients in place, the final transformation from a rotating storm to a full tornado can take only a few minutes. That short window leaves little time for forecasters to issue warnings and for people to seek shelter. Meteorologists use Doppler radar to detect rotation in storms, often spotting the mesocyclone before a tornado forms. But predicting exactly which storm will produce a tornado, and when, remains a significant challenge. Why some supercells don't produce tornadoes. This is one of the greatest puzzles in tornado research. Some supercells have all the classic signs: strong rotation, a well-defined mesocyclone, yet never spawn a tornado. Others, seemingly less organized, suddenly produce a violent twister. The answer seems to lie in the subtle details of temperature, humidity, and how the storm's downdrafts interact with the inflowing warm air. If the descending air is too cold, it can choke off the updraft. If it's just the right temperature and humidity, it can help tighten the vortex and bring it to the ground. Life cycle of a tornado. Tornadoes often follow a recognizable pattern. Organization. Rotation intensifies near the ground. Maturity. The tornado reaches maximum strength and size. Occlusion. The downdraft wraps around the vortex, cutting off the warm inflow. Dissipation. The tornado weakens and eventually fades. Some tornadoes last only a few minutes and travel a short distance. Others, known as long-track tornadoes, can stay on the ground for more than an hour and leave trails of destruction stretching over 50 to 100 miles. Forecasting and early warnings. Thanks to decades of research, tornado forecasting has improved dramatically. In the 1950s, people often had no warning at all. Today, the average lead time for a tornado warning is about 13 to 15 minutes, though in some cases, it's shorter. This progress comes from a combination of Doppler radar, storm spotters, satellite data, and sophisticated computer models. Still, the chaotic nature of storms means that forecasting tornadoes with precision remains one of meteorology's hardest tasks. Staying safe knowledge is the first line of defense. People living in tornado-prone areas, such as the U.S. Midwest and South, should know their local warning systems and have a plan. The safest place is an underground storm shelter or a basement. If that's not available, the next best option is a small, windowless interior room on the lowest floor. Emergency kits with water, food, flashlights, and first aid supplies can save lives during extended power outages or after a storm passes. Ongoing research and future discoveries. Scientists continue to chase storms, deploying radar-equipped trucks, drones, and even mobile weather balloons. These efforts have revealed details of how air flows within storms and have helped improve computer models. The ultimate goal is to predict not just which storms can produce tornadoes, but exactly when and where a tornado will form. Achieving that would give people more time to prepare and could save countless lives. A dance of nature's forces, tornadoes seem like chaotic accidents, but they result from a precise combination of natural forces: heat, moisture, wind, pressure, and timing. The delicate balance that gives birth to a tornado shows just how dynamic and interconnected our atmosphere is.